you don't use the Chinese remainder theorem, then by just guessing it, it'll consume all your time, all your exam time to reach this kind of number. Do you see? So if you just say, 27 addition to 53, and you create a set, and then you want to reach this number, then you should make a huge table to reach this number. So to run this kind of problem, you just pick these numbers, 53, 27, right? So you pick these numbers, and then create rows, right? So there are three rows, right? So you create 53, 27 row, 12, 34 row, 56, 71 row, and then you run CRAM, right? Chinese remainder. Then it will give you the solution. So to practice, you can download this file and then run. So next time is exam. So this time, anything, I will answer up to your satisfaction. I don't care whether I should spend the whole hour answering just one part or I answer 10 different, I don't care. You ask, and then I will answer up to your satisfaction. So please ask problems from the set, or general approach is okay too. So what set and what problem do you want to know? Yes?
Set F, problem 1.
I will do it. So let's solve this problem. We want to prove this fact. And as I mentioned before, when you ask to prove it, you can use anything up to that point. If you do not use the statement itself, then it's okay. Or some statement immediately the same as the statement, then it's okay. So I solve it. Because phi is multiplicative, so to prove this kind of statement, you can use the property such as this. Phi function is multiplicative. This is problem number 3, right? Problem number 3. This portion itself is problem number 3. And once it's multiplicative, then it's good enough to prove it for prime power, because we can decompose the number into prime powers and later multiply. So sum of divisor dividing prime power phi of d equals 1 divides p to the power of k, p divides p to the power of k, p squared divides p to the power of k, and p to the power of k divides p to the power of k. These are all possible divisors. And can you find other divisors than these? then by definition, phi of 1 is 1. By definition, phi of 1 is 1. And phi of p is p minus 1. Phi of p squared is p squared minus p. P of k is, phi of p to the power of k is p to the power of k minus p to the power of k minus 1. Any questions? All simple, right? If you don't understand why these are true, then I can answer up to your satisfaction. It's up to your satisfaction. Then is telescopic sum. We can cancel out this number and this number, this number and this number, this number and this number, and some number here and some number here. Then the only remaining number is p to the power of k. Then done, right? Why? Because it's multiplicative. If we prove the fact for p to the power of k, then it's good enough. So if function is multiplicative, the sum is also multiplicative, right? So we can multiply the left side, we can multiply the right side, then we can get the result. I'll do it. Is there any question on problem number 1? Then number 2. By the previous problem result and the Mobius inversion formula, phi of n equals before doing it, let's give a name. So let f of n be p of d, d divides n. Then by Mobius inversion formula, this f of n over d, mu of d, is the inversion. In other words, once you have summand, we can find the sum. So from the summand phi, we can find the sum f. The Mobius inversion formula finds the summand from the sum. So generally, summand creates the sum. But Mobius inversion formula reverses it. Mobius inversion formula creates the summand, right? Summand given here from the sum. This is the Mobius inversion formula. If you don't understand this, ask. So this is the Mobius inversion formula. And because of Mobius inversion formula, we got this. And we calculate f of n, and by the previous fact, this f of n happened to be n, right? F of n happened to be n. In other words, anything written here is the result. So f of n over d is what? F of n over d is n over d. Anything written here is written here. So we can take out n, then n is out, and then d is here. And done, right? So it is the previous statement and the Mobius inversion formula combination. But if you don't understand why this is so, ask. So from the summand, we can get the sum. So once you have a sum, we can get the summand. Summand gives us the sum. Now, sum gives us the summand, right? This is the inversion formula. So if you are fully satisfied, then you can ask. Yes?
Can you do your set C problem 2?
Set C, problem 2, right? So it is mod, power mod, right? Power mod of 2 with power 340 modulo 341, right? Then by Fermat's-Little theorem, what happens? Fermat's-Little theorem says, just a moment, this is not prime, right? So we should find phi of 341. Phi of 341 is not 341. So we will have some left over. So let's at least get the idea. This one. So let's try this. So I will solve the second problem. Phi of 341 will be calculated because of this reason. Any number, any non-zero number to the power of phi of 341 is congruent to something mod 341. And can you guess the number? Can you guess the number? The right side? Any number to the power of phi of 341 is equal to what? 1 by Euler's theorem, right? Or if it is prime, Fermat theorem. So Fermat is a special case of Euler's theorem because phi of prime is p minus 1. So let's calculate phi of 341. 341 is 31, then 1, 31, 11, right? So 11 multiplied by 31, right? And then you can write it this way. 1 minus 1 over 11, and then 1 minus 1 over 31. Of course, we can write easier way, but I'm giving you the idea. 341 multiplied 1 minus 1 over prime factors. If we calculate it, then it is 10 times 30, so 300. In other words, 2 to the power of 300 is congruent to 1 mod 341. If you don't understand this calculation, ask me.
Why did you pick 10 and 30?
I didn't pick, I calculated. Right? 11 canceled out. Right? 11 and 11 canceled out. Then 10, 31, 30. Yeah. Oh, I want to factor 341. Oh, so I can consider some small number, like 11 or 31 or something, right? I just saw that it is this, but sometimes we can try from 1 to like 2, 3, 4, 5, and so on. So you can try, for instance, 2, not even, right? 3, no, 4, no, 5, and so on. And then like 11, then you may hit 31, right? You may try 11 first. But I saw 31 first. Yes?
Well, I mean, it says calculate 2 to 3.
Oh, of course, I will go to that place using this fact. Any other questions? So I will show you the fact that if we multiply 3, then it is 1, right? Then we can break up the power this way. This is the problem, right? And then three forty. Then 2 to the power of 300 multiplied by 2 to the power of 40. And then 2 to the power of 300 is congruent to 1. And then 2 to the power of 40. Do you see? Then let's do it by binary exponentiation. It is 2 squared. So 2 is 2. 2 squared is 4. 2 to the power of 4 is 16. 2 to the power of 8 is 16 multiplied by 16. 16 multiplied by 16 is, thank you. But for some people here, I will show you how to do it without using calculator. Then we calculated 6, and then 5, and then carry over 1, 256. And 256 subtracted from this number gives us 585, right? 85. So it can be written by a smaller number, 85. Two to the power of 16 is congruent to minus 85 multiplied by minus 85, or plus 85 by multiplied by 85. So I will do the similar calculation one more time. I'm not using any calculator here. I'm doing this in all hand calculation. Five times 5 is 25. 5 times 8 is 40. 5 times 8 is 40. 8 times 8 is 64. Then 5, 2, 2, 7, right? So it's congruent to 7, 2, 2, 5, in fact equal. Then we can divide this by 341. So I will save it and go to the next column. But if you don't understand the steps, ask me. And then after doing this, we will go up one more power, because 40th power is the goal. We'll go up one more power, 32nd power. And then once we reach 32nd power, we can combine these things to create 40. This is called the binary exponentiation technique. After removing big chunks such as 300 power, right? Big chunk was removed by Euler theorem. We have smaller pieces, and then we can use binary exponentiation. So 7225, negative 85. So once we divide this by the modulus given by the problem, 341, then as you can see, 2. So to pass number theory course, you should calculate numbers well. 0, and then 4. 5, and then 1. And 341 subtracted, then it gives us 4, 6, 64. 64, right? We are handling congruence mod 341. Any questions? Then one more time. 64 multiplied by 64. This might be some number that you are familiar with. But in any case, let's calculate. Then 6, 9, and then 0, 4, right? 2 to the power 32 is congruent to 64 squared is congruent to, is equal to, in fact, 404096. And then we can divide. I will remove this simple division because you can always divide numbers. (4096) divided by 341 gives us 1, 341, and then subtraction gives us 8, and then 6, about 2, right? 6, 8, 2, then 4. So it gives us 4. Then we are almost there. 2 to the power of 40 can be, 2 to the power of 40 can be rewritten by binary exponentiation. 2 to the power of 40 is congruent to 2 to the power of 32. We are using just this list. 16 is too big. If we had 16, then we cannot get that. So 8 right? 2 to the power of 8. Then 8, and then 32 gives us 40. This is it. So it is congruent to 4 multiplied by negative 85. Then 85 multiplied by 4, 20. Then 340, right? Negative 340. And it is 1 mod 341. So it is 1. So I showed you all steps. The first step is removing big portion using phi function because of the reason that I explained. So I will rewrite the steps in summary. 2 to the power of 340 is equal to 2 to the power of 300 multiplied by 2 to the power of 40. And by Euler theorem, it's congruent to 1. And then now we decompose this using binary exponentiation. And then we now have 1 multiplied by 2 to the power of 32 multiplied by this number. And then this number happened to be negative 340. And negative 340 o'clock is the same as 1 o'clock in this system. So we got the result. Doesn't matter. It's just the same, congruent, right? Like 11 o'clock is the same as negative 1 o'clock. So please check all the necessary steps and ask questions. By the way, how did the text solve the problem? It was page number 90. I see. It found that 11th power gives us 10th power. Right, 10th power gives us 10th power gives us 1. I didn't know that. So text knew about 10th power, but I didn't know 10th power. Because in binary exponentiation, 10th power was ignored. So textbook approach was finding 2 to the power of 10. 2 to the power of 10 happened to be 1. Then suddenly, as you can see, 10th power is already 1. Then 10th power to the 34th power. So that means 30 multiplies 34 times. So it has an easier solution. My solution is from the principle. The text solution is from experience. But doesn't matter. No matter what you use, if you get this result, you'll get full credit. Yes?
Can you set F number 5?
Order is the one that you want to find. Find the order of 2 mod 13. So let's do it. 2 to the power of 1 is 2. 2 to the power of 2 is 4. 2 to the power of 3 is 2 to the power of 3 is 8. 8 is congruent to negative 5. We are considering mod 13. 2 to the power of 4 equals 16. 4 multiplied by 16. And then 16 o'clock is the same as 3 o'clock. 2 to the power of 5 equals 2 to the power of 5 equals, multiplying these numbers, negative 15. Negative 15 o'clock is the same as negative 2 o'clock. Excuse me? Sorry. Yeah, then you lose point, right? 2 times 3 is 6. Simple. And then 2 to the power of 6 equals Negative 5 multiplied by negative 5 gives us 25. And 25 o'clock is the same as negative 1 o'clock. Right? 2 to the power of 7 is equal to negative 6. 2 to the power of, I'm just showing you all possible cases and then give you the better approach. So this isn't the best approach, but it explains the order. 6.
When you did 2 to the third, that was 8. You made that minus 5 to the...
Smaller number. I want to use smaller number.
Okay, so the key is go to the smaller number even if it's the negative sign.
Right. Absolute value is smaller, then the multiplication is easier, right? If the absolute value is smaller, the multiplication is easier, but you don't have to. If you can handle big numbers, then handle big numbers.
Why is 2 to the 7? Why is that negative 6?
So, thank you. 7 is equal to negative 2. And then negative 2 multiplied by 2 is negative 4. Negative 4 multiplied to negative 8. Negative 8 is congruent to 5, right? 2 to the power of 10 is multiplied by this by 2. 10 is congruent to negative 3. 2 to the power of 11 is multiplying this by 2, then negative 6. And then 2 to the power of 12 is negative 6 multiplied negative 6. Negative 12, right? Negative 2. And then negative 12 is congruent to 1. So, because of this fact, the order of 2 is what? Because of this fact, order is 12, right? Order is, by definition, this power, giving us 1. The smallest possible power giving us 1 is called the order. But in reality, you don't follow my approach. What can you do? You can streamline the approach by using the principle that order divides phi of n. Order should divide phi of n. Then the order should divide phi of n, phi of 13, which happen to be 12. Right? Order should divide 12. In other words, you don't have to worry about 5. Right? You don't have to worry about 7. Right? You worry about 1, 2, 3, 4, 1, 2, 3, 4, 6, and then 12. But I showed you all the cases to convince you. But in reality, you don't have to calculate all possible powers. In reality, order should divide phi of that number. Phi of Rice modulus. So if you are satisfied, then it's good. If you are not, then ask more on this problem. Then I want to question you. How many, first of all, is 2 a primitive root? Is 2 a primitive root of 13? Is 2 a primitive root of 13 or not? Yes. Why? Because it achieves that number when the power is p of 13, right? And the power is p of 13, which happens to 12. So 12 is the smallest number possible achieving it. That kind of number is called primitive roots. So 13 has a primitive root. You already know the principle. Then how many primitive roots does 13 have? So the total number of primitive roots of 13 is equal to phi of 13, then phi of 12, and then phi of 12 is 12 multiplied by 1 minus 1/2, 1 minus 1/3. Then it is 12 multiplied by 1/2 multiplied by 2/3, and total 4 primitive roots. 2 is one of them, right? 2 is one of them. So 2 and some number, and then some number. So total 4 primitive roots. So let's check what numbers are primitive roots. What do you mean?
What are the primitive roots of
There is no easier way. The number of numbers, right, each number. So the number of number is has an easy way, but other number yes.
Why did you choose 2 and 3? Or why did one have
That is from the principle. Phi of, once you multiply phi of, for instance, any prime power, right? Prime k1 power, right? Prime to k2 power, and then prime r to the kr power. Then these numbers multiply by 1 minus 1 over p1, 1 minus 1 over p2, and then 1 minus 1 over pr is the principle to calculate phi function. So 12 is 2 to the power of 2 multiplied by 3. So we divide 1 minus 2 and 3, right? 2 and 3. I'm waiting.
set C number 3?
Set C number 3. You don't have enough space. I'll go to the new page. Is it this is
Number 4.
you meant number 4?
That's fine.
You meant number 4, right?
You just actually both are good. 3 and 4.
Yeah. So I will solve. But I didn't cut this portion. So I will recut it because the problem was cut. This is the problem. So let's solve this problem. Mod P is assumed. So I'm proving it, and to prove it, I will use Wilson theorem. And Wilson theorem says this fact. If you multiply 1 through P minus 1 for a prime number, then it is congruent to -1. I proved it. Then now, because P is congruent to 1, mod 4, P minus 1 is divided by what? Because of this fact, I can say this equivalent statement. What is the equivalent statement to this one? P is congruent to mod 4 is equivalent to saying what? P minus 1 is divided by what? 4, right? These are equivalent, right? This is the very definition of modulus statement, right? Modulus statement. So P minus 1 is multiplied by 4. So we can break this up into two parts. One, two, up to P minus 1 over 2. P minus 1. So I multiplied the numbers, not in a row, but in a column. So I'm multiplying all these numbers in a column. Then, as you can see, if I multiply these numbers, then it will give us minus 1 squared. Do you see it? If I multiply these two numbers, I'm multiplying all these numbers from 1 through P minus 1 in any order, right? So I'm multiplying it this way, then minus 2 squared. If you don't see why, ask me.
I don't see why.
So let's do it. Generally, I arrange them this way. When k happens here, I wrote down p minus k. Then let's multiply. Is it very difficult? If I multiply this number, then it's pk minus k squared. Then with mod p, p times something is gone. So generally, if I multiply k and then p minus k, because of mod p, p is gone, then minus k squared. So for each row, we get this statement up to this end. Then it is, minus should be outside. I made a mistake. Minus should be outside, and then p minus 1 over 2 squared. So there are 4 times some number. So here we made pairs, but in each column, do we have even number of numbers or even odd number of numbers? Odd number of rows or even number of rows, because it's 4k. Because take a look, p minus 1, 1 through p minus 1, the number of numbers 1 through p minus 1 divided by 4, we paired them. After pairing them, we had rows. Because it's divided by 4, is this even number of rows or odd number of rows? Even number of rows, right? That means there are even number of minus signs. So it means if I multiply the left side, then minus 1 and then even power, right? And then 1 squared, 2 squared, up to p minus 1 over 2 squared, and the right side is 1 by Wilson's theorem. Right? So after this, we can get rid of negative 1 to the even power. Negative 1 to the even power is 1, right? And then we can rewrite it using 1, 2, up to p minus 1 squared, and then we can rewrite it. Let's call x, right? 1 multiplied by 2 multiplied by this number. Then what happens? 1 multiplied by x squared plus 1 is 0. Or we can get rid of this 1. Then, as you can see, we not only proved the case, we found the solution. Solution is what? 1 through the half, right? 1 multiplied through the half. So you now clearly see why the requirement p is congruent to 1 is there. If it is odd, what happens? If this is odd, then this negative will survive. Then this negative and negative will cancel each other out. Right? Then we don't have special result in this direction. So please check why this lead to the solution. Why this fact or this fact lead to a solution.
I don't understand the last. So you go, I understand the 1 times 1 times 2.
Yeah.
B to the minus
Right.
squared, your minus 1. So then x is what's in parentheses.
Mm-hmm.
So then x squared.
So I not only proved it, I found the solution. Solution is multiplying the number 1 through the half, right? 1 through the half. That is the solution x. So not only existence is shown, but how to find the solution is shown too. So let's make up. So what prime has this congruence? Some prime having this congruence. So please find some prime having this congruence. What number? P is what? 5, right? Then, because of this fact, what is x? X should be equal to what? 1 times p minus 1 over 2. P minus 1 is 4 over 2. 2 is the solution. 2 squared is what? 4. 4 plus 1 is what? 0, mod 5. Or p is, for instance, 13, right? P is 13. Then x is what? 13 minus 1 divided by 2 is what? 13 minus 1 divided by 6, right? So 1, 2, 3, 4, 5, 6. This is the solution to the problem, mod 13. So it not only proves the theorem, but also gives you the idea to find the solution x. Up to your satisfaction, I will answer. So please ask or check what part you don't understand. By the way, what if it fails? In other words, P is not congruent to 1. Then will this happen? P is not congruent to 1, mod 4. Will this happen? For instance, what prime satisfies this condition? For instance, prime number equal to 3, odd prime. We are considering odd prime. Right? This prime doesn't satisfy the condition. Then, as you can see, 0 squared plus 1 is congruent to 1. 1 squared plus 1 is congruent to 2. 2 squared plus 1 is congruent to 4 plus 1 is congruent to 5. 5 is congruent to 2. So it cannot happen, right? When it is 3. Of course, P equal to 2, then 0 squared plus 1 is congruent to 1. 1 squared plus 1.
How did you get that 5 is congruent to 2? Is it 1?
5 is,
So 1, 4.
mod is 3. P. Right. 5 o'clock is the same as 2 o'clock, right? So it is for odd prime, not for even prime. When I tried even, I found the solution. So it is for odd prime. So for instance, P equals to 7. P equal to 7, then it doesn't happen. Let's do it. P equal to 7, then 0 squared plus 1 is 1. We should get 0, right? We should get 0 here, but we don't get 0. 1 squared plus 1 is 2. 2 squared plus 1 is 5. 3 squared plus 1 is 9 plus 1, 10. 10 is congruent to 3. 4 squared plus 1 is 16 plus 1, 17. Then 14 is extracted 3. 5 squared plus 1 is 25 plus 1, 26. 26 is the same as 21 and then 5. 6 squared plus 1 is 36 plus 1, 37. Then, as you can see, 20, 35, then 2. As you can see, we can look at 0, no matter what, right? In the, with mod 7, there are 7 legitimate numbers, right? 0 through 6, 7 legitimate numbers are all plugged in. We didn't get any result to the problem, right? Any solution to the problem. So only when P is congruent to 1, mod 4, we have solution when it's an odd prime. When it's an even prime is just 2. So for even prime, let's check. P equal to is trivial case. When P is equal to 2, 0 squared plus 1 is 1. Right? And then 1 squared plus 1 is 2, and 2 is congruent to 0. Right? So when it is 2, we have a solution. But it is very trivial, right? This is very trivial. So we don't have any value in this portion. So we eliminate the even prime and then create the theorem for odd prime number. So do you see the crux of this theorem? The crux of the theorem is when it is an odd prime, of course this itself means odd, right? Then it has a solution. And in fact, the reverse is true for odd prime. The reverse is true for odd primes. So please find, even in the explanation you can find and ask. Please find and then. So do you see the clue? Once it is even, it's too trivial, so we don't even have to mention about even prime. There is only one even prime, 2, right? So we don't have to worry about 2. Then for all other primes, this is bidirectional. If this happens, x squared plus 1 has a solution. If x squared plus 1 has a solution, then it is a prime of this sort. Both directions are possible. I showed you only one direction. The other direction can be shown too. Yes?
Can you do a problem using Fermat's theorem?
So it's like this. Give me a prime, for instance, 11. Then phi of 11 is what? 10, right? So any number, pick any number, like 4 to the power of phi of 11 is congruent to 1 mod 11. This is called Fermat's theorem. So any number, any non-zero number, of course if it is zero number, 0 to the power, we multiply 0 many, many times, it's still 0. Then it cannot be 1. So if you exclude 0, then for any number, this happens. It is the special case of Euler theorem, right? Euler theorem. This is called Fermat's little theorem, right? No matter what number you pick, the number to the power of p is congruent to 1 mod p. So assume that you are asked to answer this question. Oh, for instance, 37 is prime. So find this number. Find this number. Then what is it? With mod 37, what is this number? Because of Fermat's little theorem, this number is what? 1. In fact, when I took the number theory course, I couldn't remember Fermat's theorem there, and I tried to calculate 17 to the power of something similar to this by using calculator. The professor allowed a calculator. So I tried, I failed. I used up all my time, and then I got error. I should have known Fermat's little theorem and then applied, and it is like 1 minute problem. It was 1 minute problem, but I didn't remember, unfortunately. So I used my calculator to find the number, failed, and spent all my time. On the exam, anything can happen, right? Anything that can go wrong will go wrong. So this is Fermat's little term, right? Or a little bit tweaked version. Let's tweak. 17 to the power of 37. Oh, it's not Fermat's little term. Then apply it. How? It is equal to 17, 36, and then 17. Do you see it? Right? So even though it's not the raw form of Fermat's little theorem, you can apply it. Then after this, then this gives 1 and then 17, and the answer is 17, right? Mod 37. Or even 38 is possible, right? So you can apply Fermat's little theorem, but the general form is Euler's theorem, right? So you can apply generally Euler's theorem to remove a big chunk and then handle smaller pieces. So you have about 15 more minutes. Ask as many as possible, or as deep as possible. Yes?
Set B number 4.
Set B number 4. So if A is congruent to 0, then the left-hand side is 0, and then right-hand side is also 0, so it is done, right? When A is congruent to 0, then the left-hand side is 0, right-hand side is 0, so they are equal. If A is not congruent to 0, then by Fermat's theorem, A to the power of phi of P, or Euler theorem, is 1, right? By Euler theorem or Fermat's little theorem, doesn't matter. Because P is prime, phi of P is P minus 1. Then we can multiply both sides by A, then A to the power of P is congruent to A, mod P, done, right? So if it is prime, if you do A to the power of P, then it's the same as A. Don't believe it? Believe it. I will show you. You may pick any prime number. I will wait. You may pick any prime number. So let's pick pretty large one. 131 sounds like prime, right? 131. 131 is prime, right? So let's do it. Any number below 131, like 129, right? 129 mod. So we can calculate the power of 129 with 131. Do you see? We are doing 129 to the power of 131 mod 139. Then what will be the result? Without even checking it, what is it? What is the result then? 129. Computer didn't know. It just calculated, and what do we know? Because we know the theory. You don't believe it? Then I can convert this into any number A, and then I can use A equal to something. A equal to 17, right? And then let's do it. A equal to 18, or in fact, if it is below 131, it's okay. So 111, 11. So no matter what number you use, that number to the power of p is congruent to that number mod p. That is the term.
But A has to be smaller than B?
Because if A is, if A is like 132,
Right.
then 132 is congruent to 1. So it is useless consideration if we consider. It's possible because 1 is the same as 140. So I'm not saying it's wrong, but it's a little bit awkward. So please check and ask. So about the end of the exam time on Wednesday, I will post the solution at some place because online students will take the exam on Wednesday, Thursday, and Friday, and so on. I will not reveal it to general public, but I will inform you of the solution that you can find, or if it's possible, I can even print out the solution.
Have we covered all the problems on the test yet?
Let me think. Not yet. We covered some, right? At least like. There are so many I do not remember. Maybe somewhere. So please check and ask. Yes? So what set and what problem? Maybe one or two more problems. That's the max. So take your time. Slowly find one.
Pick one, you can push
I focused on theorems, big theorems. Oh, that's the one. Like such as Phis multiplication, big theorems. So there are some big theorems.
Can you do the Wilson theorem? I think
No problem. No problem. So on the exam, big theorems such as Wilson's theorem might be questioned, unfortunately. I will mention later. 1 multiplied by 2 multiplied by p minus 1 is congruent to negative 1 is Wilson's theorem. And this is equivalent to saying 1 multiplied by 2 multiplied by p minus 2 is 1. Oh, p minus 2 is 1. Nice. So one less number, then you can cancel out negative 1, right? We can cancel out negative 1. So this is the version that we use to prove Wilson theorem. Then 1 can be also cancelled out, right? So I'm removing and removing and removing so that I can make pairs. So for even prime, for p or 2, p equal to 2 or 3, trivial, right? Obvious, right? You can check 2 or 3 case. So now, suddenly, p is greater than or equal to 5 and all odd, right? So we are considering this statement for odd because other cases are trivial. Do you see? Then all we need to do is pairing these numbers to make 1. 2 times some number is congruent to 1. After removing this number, we'll have, for instance, 3 times some number, or 3 could come here then. So, and then we pair these numbers, and then eventually we will get 1s this way. So the proof part handles these, and then first of all, p is odd, right? P is odd because p is prime greater than 5. Then how many numbers are there in between these? How many numbers? Even number of numbers or odd number of numbers? Even number of integers or odd number of integers? Even number of integers, right? So at least if we make pairs, then it'll be okay to have 2 columns, right? 2 columns without empty spot. But sometimes people wonder, what if something like this happens, right? What if something like this happens? In other words, to prove the statement, we should avoid this situation. So to do it, I will use this fact. If x squared is equal to 1, right? If x squared is equal to 1, then mod p. This is equivalent to saying what? X squared minus 1 is divided by p, right? X squared minus 1 can be factored. X plus 1, x minus 1 is divided by p. Then this, because p is prime, p divides x plus 1, or p should divide x minus 1, and this is equivalent to saying p is congruent to negative 1, or p is congruent to 1. In other words, this happens, x. This happens only when x is 1 or p minus 1, right? X is 1 or p minus 1. But I got rid of 1 and p minus 1 in the step. Take a look. I got rid of 1 and p minus 1. All we have is from numbers from 1 through p minus. So possibility was eliminated. In other words, there is no possibility that one number is squared. Then this is the situation. There are even number of numbers, and then even number of numbers are paired. But there is nothing having self-pair, right? There is nothing having self-pair. In other words, there are even number of numbers. You pick one. Then there is a pair creating multiplication equal to 1, right? And then there is another one, and then creating multiplication equal to 1, right? So by these steps, we can get rid of all these numbers, and then because of this reason, all the numbers are rearranged. Like this. 2 through p minus 2 multiplied for some pairs will create 1. Then final consideration. What if someone doesn't have a pair? You went to a party. There is no partner, right? In this number system, it doesn't happen. So assume that A is not 0, then A times X is congruent to 1, mod P has a solution. Why? GCD of A and P is what? GCD of A and P is what? 1. And mathematical expression of this concept is what? GCD of A and P equals 1 is what? AX plus PY equals 1. There are some X and Y integers. In other words, when there is a person, there is a partner, right? There's a partner. And in fact, this partner is unique. Because P is prime, X is unique. So always, there are even number of numbers. And then for each person, absolutely there is one partner. That means we can pair them with partners to create. And there is no one-to-many partner situation because it's unique, right? Once you have A, this is unique. In other words, if you have X prime or Y, or K satisfying the same congruence, then K and X are congruent. In other words, by this statement, we have filled all these numbers and then create congruent one by pairs, right? By pairing. But difficult part to explain the proof is the concept, because we cannot give you concrete examples such as 1 through, multiply 1 through half. We cannot give you concrete example, but it's in our concept. We have number, then pick one number, then there is a partner that we cannot change. Forced partner, right? Here, then forced partner, right? And then there are even number of numbers, and there is no self-partnering. So because of this, we are it's a little bit tougher. So unfortunately, this isn't asked, because if I asked, then you may have hard time explaining all. But in any case, it's a good review problem. So let's stop it here. If you have more questions, you can approach and